In the reaction we are attempting to describe, which is an addition of a positron with an electron into an antimuon and a muon, we see that we have two antiparticles, the positron and the antimuon. So we need to see how these antiparticles arise from field theory. And we will do that in the framework of classical field theory, because it turns out we don't need the quantum aspect in order to see antiparticles. And we will do that not in the case of fermionic fields like here. We will do that with a non-Hermitian classical field. And we also don't need interaction, so the field obeys the Klein-Gordon Lagrangian. Because we are in a classical field theory, we can find the equation of motion by plugging this Lagrangian into the Euler-Lagrange equation. And what we get are the Klein-Gordon equations for both phi and phi star. The solution to these equations can take the form of a sum of plane waves. We will verify that this is indeed the solution of the Klein-Gordon equation. However, before we do that, just notice that A and B do not have to be the same thing, because we start with a non-Hermitian field and therefore phi doesn't have to be a real. So A and B are independent components. Let's first check that this is solution to the Klein-Gordon equation in the case of B equal to 0. The time derivative and the special derivative will act on the exponential and will respectively bring down minus I omega k and ik. And we see that by imposing that omega k is equal to square root of k squared plus m squared, this quantity is just 0. Of course, it works the same way for b non-equal to 0, because we have the same form of the exponent up to a sign. We have omega kt minus kx, which brings this condition, and therefore this is solution to the Klein-Gordon equation. Note that the square root term in the denominator here is only here for normalization purpose. It's not necessary in order to have phi being a solution of the Klein-Gordon equation. In fact, the square root of omega k is necessary in order to ensure that the volume element in momentum space transforms properly under Lorentz transformation. Before going further, let us mention a small historical note. The Klein-Gordon equation was first introduced in the framework of relativistic quantum mechanics. And in this case, phi denotes the wave function for a particle. And we see that we have a sum of plane waves, which are in the first case with a positive energy, because remember that in quantum mechanics we have something which goes like exponential minus I e t. So the energy is defined as minus the time frequency for a plane wave. However, in the second term we see that we have a plus I omega k t, and omega k is positive. Therefore, this second term corresponds to a negative energy solution in the interpretation of relativistic quantum mechanics. But now in field theory, omega k just represents a time frequency, and it doesn't matter if we have a positive or negative time frequency. This is not necessarily associated to an energy. We will come back later to the actual energy carried by this negative frequency solution. For now, let's just notice that we have a sum of two components associated with the amplitudes A and B. And because the field is non-Hermitian, A and B are just independent quantities, and therefore they can describe different objects. We are going to call the disturbance of the field which propagates with amplitude A particles, and those which propagate with amplitude B antiparticles. Of course, for now these are just named, but we will see soon that these indeed correspond to physical particles and antiparticles. And in order to see that they correspond to different physical objects, we will invoke Noether's theorem. So we first need to seek for symmetries of our Lagrangian, and then calculate the corresponding conserved current and conserved charges, and show that for particles and antiparticles, the associated charges may be different. And naturally, an obvious symmetry of this Lagrangian is a global gauge invariance we have studied earlier. We see that under these transformations, the Klein-Gordon Lagrangian is unchanged. Therefore, this is a symmetry for the system. We already determined what is the conserved current for this symmetry and this Lagrangian. So all we need to do is to calculate this charge for a particle and for an antiparticle. So it doesn't matter what the actual form of A of k or B of k is, so we can just pick up one plane wave, and for convenience we are going to choose. So only one momentum survives when we plug in this expression for A in the expression for phi. We need to calculate J0 with this expression for phi. Of course, the integral over the volume will give an infinite. That's because we have a plane wave. However, it doesn't really matter because what we just want to compare between particles and antiparticles is the sign of the charge. So we got a negative charge for the particle. Now let's do the same thing in the case of an antiparticle, assuming a plane wave. So we see that particles and antiparticles have opposite charges. Therefore, they do not correspond to the same physical object. Of course, they come from the excitation of the same field. Therefore, they must have the same mass. We still need to check what the energy of the particles and antiparticles is. Indeed, in the case of relativistic quantum mechanics, what we had was a negative energy solution associated to the antiparticles. Is it still the case in quantum field theory? So in order to get the energy, we need to first recognize the symmetry associated to the Lagrangian, which is associated with time translation in space. And from that, we will calculate the conserved Noether charge, which is the energy, and show that indeed it's positive for both particles and antiparticles. Here the energy is defined from the energy momentum tensor, its time-like component and the space integral of it. And as before, what we have is the space integral of the Hamiltonian. However, now we have in fact two fields. We have phi and phi star. Therefore, we have two terms to sum over in order to get the Hamiltonian. So we now need to replace the Lagrangian by its expression, and from that we will get the energy. No need to replace these quantities by the actual expression for the field, neither to integrate over volume, because what we see is that we are just having a sum of positive defined terms. Therefore, the energy, whether it is for a particle or an antiparticle, because we didn't define the difference here, has to be positive. Therefore, the negative energy solution, which we had in relativistic quantum mechanics, are not here anymore in field theory. And to do that, we only had to do it in classical field theory. We didn't even need to invoke a quantum aspect. And indeed, what we find at the end is that we have positive and negative frequency, time frequency solution for the free Klein-Gordon Lagrangian. And the positive frequency are associated with particles, while the negative frequency are associated with antiparticles, but both have a positive energy. We also saw that because they are excitation of the same field, they must have the same mass. But what differentiates them physically is their charge. According to Noether's theorem, we found out that the charge for antiparticles and for particles have opposite sign. So we showed that in the case of the charge associated with the symmetry under global gauge invariance, but it turns out that every charge associated with any symmetry will have an opposite sign for particles and for antiparticles.